Control valves are critical components in various industrial processes, including manufacturing, oil and gas production, water treatment, and power generation. They come in various designs and sizes, tailored to specific functions and operational conditions. The most common types of control valves include ball valves, butterfly valves, globe valves, and diaphragm valves, each with unique characteristics suited to particular applications. What is a control valve? A control valve is a mechanical device used to regulate or manipulate the flow of fluids, such as gas, oil, water, and steam, within a system. It operates by varying the size of the flow passage as directed by a signal from a controller, enabling direct control of flow rate and consequently the process variables such as pressure, temperature, and liquid level. The primary components of a control valve include the valve body, the internal trim parts such as the valve seat, plug and stem, and the actuator. The actuator, which can be pneumatic, hydraulic, electric, or manual, is responsible for moving the valve's internal components to adjust the flow passage based on the control signal. Control valves are essential for ensuring process efficiency, safety, and reliability by maintaining desired process conditions within tight tolerances and responding to system demands promptly. Types of body control valves. Control valves come in various types, each designed for specific functionalities, applications, and flow characteristics. The main types of control valves include globe valves, characterized by a spherical body and a linear motion disc. Globe valves are used for regulating flow in a pipeline. They offer precise flow control and are suitable for applications that require frequent throttling. Globe valves can be further divided into three main types based on their internal body design: T-pattern, angle pattern, and Y-pattern. Ball valves. Known for their spherical disc, the part of the valve which controls the flow through it, ball valves are used in applications requiring tight shutoff and are capable of throttling services, although they are primarily used for on-off control. They are durable and usually work to achieve perfect shutoff even after years of disuse. Butterfly valves. Featuring a disc that rotates around a central axis, butterfly valves are used for isolating or regulating flow. They are known for their compact design and low-pressure drop, making them suitable for large volume and high-flow applications. Gate valves. Utilizing a flat gate to open and close the flow path, gate valves are primarily used for on-off control rather than flow regulation. They are ideal for applications where a straight-line flow of fluid and minimum flow restriction are needed. Diaphragm valves. These valves use a flexible diaphragm that comes into contact with the bottom of the valve body to control flow. Diaphragm valves are particularly useful in applications involving corrosive fluids, fibrous slurries, or substances that require a high level of purity. Pinch valves. Employing a pinching mechanism and a sleeve of molded rubber or synthetic material, pinch valves control the flow by pinching the flexible membrane. They are ideal for handling slurries, liquids with large amounts of suspended solids, and other applications where other valves might clog. Plug valves. Featuring a cylindrical or tapered plug with one or more hollow passageways going sideways through the plug, plug valves allow fluid to flow through the plug when the valve is open. They are used for on-off control, but can provide some flow regulation at partial opening. Needle valves. With a small port and a threaded, needle-shaped plunger, needle valves are used to precisely control flow rates, making them ideal for delicate gauging applications that require precise flow regulation. Each type of control valve has its unique advantages, limitations, and suitability for different process conditions, including pressure, temperature, flow rate, and the nature of the fluid being controlled. The selection of a control valve type depends on the specific requirements of the application, including the need for precise control, durability, resistance to corrosive materials, and the ability to handle high-pressure differentials. Control valve actuator. A control valve actuator is a device that operates the valve's moving parts to modulate or control the flow of fluid through the valve based on the input from the control system. The actuator plays a critical role in the functionality of a control valve, converting the control signal into mechanical motion to adjust the position of the valve element, such as a ball, plug, or disc, and thereby regulate the flow passage. There are several types of actuators used with control valves, each with its own operational mechanism and application suitability. 1. Pneumatic actuators. These are the most common type of actuators in process industries. They use air pressure to create the force required to move the valve stem. Pneumatic actuators are known for their reliability, simplicity, and fast response times. They can be spring return types, which use a spring to return the valve to its original position when air pressure is removed, or double-acting types, which use air to open and close the valve. 2. Electric actuators. Electric actuators use an electric motor to generate the torque needed to operate the valve. They are suitable for precise control and are often used in applications where compressed air is not readily available. Electric actuators can be equipped with various types of motor controls for position sensing, allowing for precise control and feedback. 3. Hydraulic actuators. These actuators use fluid pressure to move the valve component. They are typically used in applications requiring high force and where precise control is necessary. Hydraulic actuators can provide a high power-to-size ratio, making them suitable for heavy-duty applications. 4. Manual actuators. Manual actuators involve hand-operated mechanisms like levers, wheels, or gears to move the valve. They are simple and cost-effective but require manual intervention for operation and are not suitable for remote or automated control. 5. Electro-hydraulic actuators. Combining the benefits of electric and hydraulic actuators, electro-hydraulic systems use an electric motor to drive a hydraulic pump, which then moves the valve. This type of actuator is used in applications that require the precision of hydraulic control with the convenience of electric power. 6. Solenoid actuators. Solenoid actuators use electromagnetic solenoids to operate the valve. They are typically used for on-off control rather than for modulating flow and are well suited for low-power applications. The choice of actuator depends on various factors, including the required force or torque, control precision, response speed, available power sources, environmental conditions, and the specific needs of the application. Proper selection and maintenance of actuators are crucial for the reliable and efficient operation of control valves in industrial processes. Principal operation of control valve. The principal operation of a control valve involves modulating the flow of fluid in a process system to regulate process variables such as pressure, temperature, and fluid level. Control valves achieve this by altering the flow area through which the fluid passes, thereby affecting the flow rate. The basic operational steps can be outlined as follows. Receiving a control signal. The operation begins with the control valve receiving a signal from a control system. This signal represents the desired set point or operational condition that the process should maintain. The control signal is typically an electrical, pneumatic, or hydraulic input, depending on the type of valve actuator. Actuator response. The actuator, which is connected to the control valve, responds to this control signal. The actuator's job is to convert the control signal into mechanical motion. For instance, in a pneumatic actuator, the control signal adjusts the air pressure to move the actuator's diaphragm or piston, which in turn moves the valve stem. Valve stem movement. The movement of the actuator is transferred to the valve stem, which is connected to the valve's internal moving parts, such as a plug, ball, or disc. This movement can be linear, up and down, or rotary, rotational, depending on the type of valve. Flow area change. As the valve's internal moving part, the plug, ball, or disc, moves in response to the actuator, it alters the size of the opening, or orifice, through which the fluid passes. Opening the valve increases the flow area, allowing more fluid to pass through, which increases the flow rate. Conversely, closing the valve decreases the flow area, restricting fluid flow and reducing the flow rate. Flow modulation. By precisely adjusting the position of the valve's internal moving parts, the control valve can modulate the flow rate to match the desired set point or operational condition dictated by the control system. This modulation helps maintain the required process conditions, such as keeping the pressure within a pipeline at a specific level or maintaining a certain temperature in a reactor. Feedback loop. In most control systems, sensors monitor the process variables, like pressure or temperature, and send feedback to the control system. If there is a discrepancy between the actual condition and the desired set point, the control system adjusts the control signal to the valve, and the process repeats. This continuous loop ensures precise control of process variables. The operation of a control valve is integral to process control in various industries, enabling the automation of fluid handling and the maintenance of desired operational conditions with high precision and efficiency.